Ever wish you had a thermometer that was, uh, like, totally accurate, like, never needed calibration, could even measure the temperature of distant planets?
Sounds pretty sci-fi, right?
Right.
Well, it's not as far-fetched as you might think. It's a real area of research. It's called Rydberg thermometry.
Rydberg, okay.
Oh.
Lay it on me.
It uses atoms, specifically these things called Rydberg atoms, as like the ultimate temperature sensors. And we've got a bunch of research papers on this. It's some pretty mind-blowing stuff.
So we're talking atoms, like, seriously.
Seriously. We're moving away from all those limitations of, traditional thermometers, the ones that rely on things like expansion of mercury or changes in electrical resistance. Those are all tied to, like, the properties of specific materials.
Yeah, I guess so.
But Rydberg atoms, well, they're different. They tap into something way more fundamental, the interaction between light and matter, at the quantum level.
Okay, hold on. Before we go full on quantum, maybe we should back up a bit. What exactly are Rydberg atoms? What makes them so special?
Okay, so picture an atom, right?
Yeah.
Like a tiny little solar system. You've got electrons orbiting the nucleus, kind of like planets around a star.
Okay, got it.
Now, imagine one of those electrons gets like a massive energy boost, and it jumps to an orbit that's thousands of times larger than normal. That's a Rydberg atom.
Wow. So it's like supersized.
Yeah, exactly. And because those outer electrons are so far away from the nucleus, they're super sensitive to their environment, like incredibly sensitive.
So they're like the canaries in the coal mine, but for the quantum world.
Exactly. Any little change in their surroundings, like a tiny temperature fluctuation, can cause these electrons to like jump between energy levels. It's like a tiny quantum leap.
Okay, I think I'm starting to get it.
Mhm.
But how does this actually translate to measuring temperature? I mean, we can't just like stick a Rydberg atom on our forehead and get a reading, right?
Right, huh? But here's where it gets really interesting. Every object in the universe, anything with a temperature above absolute zero, it emits this thing called blackbody radiation.
Oh, I've heard of that.
Yeah, it's a spectrum of electromagnetic waves. And the hotter the object, the more intense this radiation gets.
So it's like every object has its own thermal fingerprint.
Precisely. And Rydberg atoms, they're super sensitive to this black body radiation. It can actually cause those outer electrons to jump between different energy levels, like we were talking about.
Okay, so we've got these Rydberg atoms acting like tiny little antennas.
Yeah.
They're picking up the black body radiation from their surroundings. But how do we actually, like, measure this interaction? How do we translate it into a temperature reading?
The key is the relationship between the frequency of the black body radiation and the energy levels in the Rydberg atom.
Oh, right. Energy and frequency.
Hmm.
Like back in high school physics. Is this where Planck's constant comes in? That EF equation?
Bingo.
Yeah.
Planck's constant. It's this fundamental constant in quantum mechanics. Relates the energy of a photon to its frequency. And a photon is just a tiny little packet of light energy.
So when a Rydberg atom absorbs a photon from the blackbody radiation, it causes the electron to jump to a higher energy level.
You got it. And the frequency of that photon determines exactly which energy level the electron jumps to. It's like each photon has a specific key that unlocks a particular energy level in the atom.
A cosmic lock and key system.
I like that. So by measuring which energy levels those electrons are jumping to, we can figure out the frequency of the photons hitting them, and from there, the temperature of the object emitting that radiation.
Exactly. But it's not quite that simple. We also have to factor in the rate at which these transitions are happening.
The rate, what do you mean?
Well, it's not like every photon that hits a Rydberg atom will cause a transition. The probability of it happening depends on a few things: the intensity of the radiation, the specific properties of the atom itself, stuff like that.
So we need to look at how often it happens, not just if it happens.
Precisely. And these rates are governed by something called, get this, Einstein coefficients.
Einstein coefficients. Things are getting a bit more complicated now. Yeah, they're named after, you guessed it, Albert Einstein. He kind of laid the groundwork for all of this. Back in the early 1900s, there are three main coefficients. They describe the probability of different types of transitions: absorption, spontaneous emission, and stimulated emission.
Okay, I'm going to need a little help with those three.
Sure. So think of it this way. Absorption, that's when a Rydberg atom absorbs a photon from the blackbody radiation. The electron jumps to a higher energy level. Then there's spontaneous emission. That's when the electron drops back down to a lower energy level all on its own and emits a photon in the process. And then there's stimulated emission, where a photon interacts with an already excited atom, causes the electron to drop down and emit another photon that's like identical to the first one.
So it's like the photons are Like making the electrons dance between these energy levels and the Einstein coefficients are like the rules of the dance.
That's actually a great way to put it. By carefully measuring the rates of all these different transitions, we can determine the number of photons present at each frequency, which gives us a very, very precise measurement of the blackbody radiation spectrum.
And from that spectrum, we can figure out the temperature. It's like a cosmic detective story using atoms to crack the case.
It really is. And the beauty of this whole approach is that it's directly tied to these fundamental constants, like Planck's constant, the speed of light. It doesn't rely on the properties of some specific material.
So it's like having a thermometer that's calibrated by the universe itself. No wonder it's so accurate.
Exactly. It's truly an absolute measurement. But it's not just accuracy, it's the potential for remote sensing, too.
Remote sensing, like measuring the temperature of something without actually touching it.
Yeah. Because we're detecting light, we can measure the temperature of something from a distance. Theoretically, we could even measure the temperature of a distant planet just by analyzing the blackbody radiation from its atmosphere.
Now, that's what I call a long-range thermometer. But this all sounds pretty complex. What does it actually take to build one of these Rydberg atom thermometers?
It's true. It does involve some pretty sophisticated equipment. Lasers, ultra-high vacuum chambers, sensitive detectors. Not exactly something you're going to find at your local hardware store.
Yeah, I kind of figured. Okay, so break it down for me. Why do we need lasers? Are they, like, zapping the atoms?
Not zapping exactly. They're more like the key to preparing those Rydberg atoms. We use lasers to excite those electrons to those, super high energy levels we talked about. And it has to be done with incredible precision.
We're talking about, like, finely tuned lasers that can target specific atomic transitions.
Exactly. And not just any laser will do. We need lasers that are incredibly stable so their frequency doesn't drift over time. And they have to have very narrow line widths.
Line width.
You can think of it like a laser beam that's perfectly focused, no spreading out. Even a tiny wobble in that laser frequency could mess up our whole measurement.
Because even a little deviation would change the energy of the photons and throw off that whole lock-and-key system.
You got it. It all comes down to precision.
Okay, what about those ultra-high vacuum chambers? Why do we need to suck all the air out? Are Rydberg atoms, like, afraid of a little breeze?
Haha. Not quite. The vacuum is really important to create a perfectly pristine environment for the atoms. Remember, they're super sensitive. Any stray particles bumping into them can cause unwanted transitions, totally throws off our measurements.
So it's like creating a tiny, perfectly clean room for our Rydberg atoms to hang out in.
Right.
No pesky air molecules to mess things up.
That's a good way to think about it. We need to get those pressures billions of times lower than atmospheric pressure.
Wow, that's some serious vacuuming.
Mm-hmm.
So we've got our super precise lasers, and we put our atoms in a super clean vacuum chamber. What else is there?
The last piece is detection. We need to be able to see those tiny little atomic jumps that happen in response to the blackbody radiation.
How do you see something happening at, like, the atomic scale?
Yeah, good question. We can't just use a normal microscope. We have to rely on something called fluorescence.
Fluorescence. Like those glow-in-the-dark stars you can get for your ceiling.
Sort of. So when an electron in a Rydberg atom drops down from a higher energy level to a lower one, it can emit a photon of light. And that light is what we actually detect.
So it's like the atom gives off a little flash of light every time the electron makes a jump down the energy ladder.
Exactly. And we use really, really sensitive detectors that can pick up those tiny little flashes of light. And by analyzing the frequency and intensity of that fluorescence, we can figure out what transitions are happening and how often they're occurring.
And that tells us the temperature.
Yeah.
It's amazing that we can use atoms themselves as thermometers. So precise.
It really is. It's a testament to quantum mechanics and the people who figured out how to use these techniques.
So Rydberg thermometry is clearly not just some lab experiment.
Mm-hmm.
This is a technology that could totally change the way we measure temperature in all kinds of applications. But before we get to the applications, let's talk a bit more about the advantages that Rydberg thermometers have over those traditional ways of measuring temperature. What makes this technology so different?
That's a great question. And I think the biggest advantage, as we've touched on, is that Rydberg thermometers are inherently absolute. Their calibration is tied to those fundamental constants. It's not based on material properties that change over time.
So no more worries about our thermometers, like drifting out of calibration.
Mm-hmm.
No need to constantly recalibrate. That's huge, especially in fields where we need super precise measurements.
Absolutely. Imagine if you never had to recalibrate a thermometer. Think about the time and money you'd save, not to mention how much more accurate your results would be.
It'd be like having a ruler that always stayed the same length, no matter what. You could always trust your measurements because they're based on something unchanging.
That's exactly right. And this absolute nature of Rydberg thermometry has huge implications for metrology, the science of measurement. It could even lead to redefining the Kelvin, the unit of temperature. So it's based on these fundamental constants.
Yeah, that would be a huge change. But the advantages don't stop there, right? We talked about remote sensing. What other benefits are there?
Another big one is that they're contactless. We don't need to physically touch the thing we're measuring.
That would be super useful in a ton of situations,
Yeah.
like monitoring hazardous environments or studying delicate systems where you don't want to disturb anything.
Exactly. Think about nuclear reactors, chemical plants, volcanoes. You can't always just stick a normal thermometer in those places.
But with a Rydberg thermometer, you could be a safe distance away and still get those temperature readings.
That's the idea. We're basically using light to probe the thermal properties of something without messing with it physically.
Okay, so we've got absolute measurements, contactless readings, and incredible precision. But let's be real for a second. There have to be some limitations or challenges, right?
Of course, no technology is perfect. And with Rydberg thermometry, a lot of the challenges come from how complex the experimental setup is. Lasers, vacuum chambers, sensitive detectors. It's a pretty sophisticated system.
And
Expensive.
So it's not like we're going to see Rydberg thermometers in every home anytime soon.
Probably not. Not yet, anyway. But remember what happened with atomic clocks? They used to be these huge room-sized contraptions, but now we've got them in our phones and GPS satellites.
So you're thinking miniaturization is the key to make it more affordable and accessible.
Exactly. And researchers are working on it. One really promising area is using integrated photonic chips.
Photonic chips sounds futuristic.
Think of it as a miniature laboratory on a chip. It can guide and manipulate light with incredible precision, just like electronic circuits handle electricity.
So instead of having all these lasers and optics, you could just integrate everything onto a tiny chip.
That's the idea. It would make the whole system way smaller, cheaper, and use less power. It's one of the most exciting areas of research in the field.
It sounds like photonic chips could be a game changer for Rydberg thermometry. What are some of the other challenges? What are researchers working on right now?
One challenge is keeping those ultra-high vacuum conditions stable over long periods of time. Any leaks or contamination, and the system's performance goes down.
So it's not just about getting to those super low pressures, it's about maintaining them.
Right. It takes some serious engineering, careful material choices, and a lot of attention to detail.
Are there other things that could affect the measurements? Other sources of uncertainty?
Yeah, one is the Doppler effect. It comes from the motion of the atoms. Even though we cool them down to crazy low temperatures, they still move around a little, and that can make the spectral lines broader and introduce uncertainty into the measurements.
So it's like trying to hit a moving target with those lasers.
Good analogy. Researchers are figuring out ways to deal with this, like laser cooling methods that slow the atoms down even more.
So it's all about minimizing any possible sources of error. Sounds pretty intense.
It is. But the potential of this technology is worth it. Rydberg thermometry could have applications in so many different fields. The challenges are definitely worth tackling. Welcome back. So are you ready to dig into some of the applications for this Rydberg thermometry?
You bet. Last time you were talking about measuring the temperature of distant planets
Yeah.
and even looking inside nuclear reactors.
Yeah. Those are just a couple of the possibilities. I mean, this field is just exploding with potential. We're only just starting to see what we can do.
So big picture, what are some of the areas where Rydberg thermometry could really make a difference?
Well, one of the most exciting areas is metrology, the science of measurement.
Right. Making sure our measurements are accurate.
Exactly. And Rydberg thermometers, they offer this incredible level of accuracy and precision, way beyond what we can do with traditional methods. We might even be able to redefine the Kelvin, the fundamental unit of temperature, base it on universal constants instead of the properties of specific materials.
Whoa, that's huge. It'd be like rewriting the rules for how we measure temperature. So what other fields could this technology change?
Well, industrial process control is a big one. A lot of industries like semiconductor manufacturing, pharmaceuticals, food processing, they need really precise temperature control. Even tiny changes can mess things up, affect the quality, the safety.
Right, a few degrees off and your batch is ruined.
Exactly. So instead of relying on those old thermometers that drift and need constant calibration, We could use Rydberg thermometers. They'd give you rock-solid measurements, really consistent and reliable.
No more worrying about whether your thermometer is telling the truth.
Hmm?
I like it. So you're saying we could even monitor places that are dangerous or hard to get to?
Yeah, exactly. Since they're contactless, we could use them in environments where it's just too risky to put in a regular sensor. Like imagine monitoring the temperature inside a nuclear reactor or a chemical plant. You get real-time data, but you don't have to put people in danger.
That makes a ton of sense. What about scientific research? Where could this tech lead to new discoveries?
Oh man, the possibilities are pretty much endless. Like in astrophysics, we could use these thermometers to study the temperature of distant stars and planets, get a better understanding of how celestial objects form and evolve.
It's like having a thermometer that can reach across space. Okay, what about here on Earth? Any uses closer to home?
Definitely. Think about climate science. We could create super accurate temperature maps of the Earth's surface and atmosphere.
So we have a better handle on how climate change is impacting our planet.
Exactly. And because these things are so sensitive, we could even use them to pick up those really subtle temperature variations in fragile ecosystems. That could help us figure out how climate change is affecting biodiversity.
So Rydberg thermometers could be vital for environmental monitoring and conservation. But it's not just about these large-scale measurements, is it? Could we use this to look at really small things too?
Oh, absolutely. Rydberg thermometers can measure temperature variations at the nanoscale, like insanely small. So that opens up all sorts of crazy possibilities in material science, nanotechnology.
So studying how heat flows at the atomic level. Or even developing new ways to manage heat.
Yeah. Or, how about this? Imagine measuring the temperature inside a single cell. It could give us insights into how cells regulate their own temperature and how temperature affects those biological processes.
Whoa, that's mind-blowing. A thermometer that can zoom in on the building blocks of life. Okay, so we've talked a lot about what we can do now, but what about the future? Where do you see this tech going in the next, say, 5, 10, 20 years?
Oh man, the future's looking bright for Rydberg thermometry. Like we were talking about earlier, miniaturization is going to be huge. Those photonic chips,
Oh
remember?
yeah, those tiny labs on a chip.
Yeah.
So what happens when we've got those miniaturized devices? What will we be able to do?
Well, for one, they'll be a lot easier to use, more portable, way less expensive, and more people will be able to get their hands on them. I can see handheld Rydberg thermometers for field work, environmental monitoring, maybe even medical diagnostic.
Quantum level precision in a device that fits in your hand. That's amazing. What else is coming down the pipeline?
Another area that's really exciting is what we call ultra-fast Rydberg thermometry. Instead of using those continuous wave lasers, we can use these super short pulses of light. We're talking femtoseconds.
Wait, remind me, how short is a femtosecond?
It's a millionth of a billionth of a second, so super, super short.
Okay, got it. So why are these super short pulses useful for measuring temperature?
Well, they allow us to see the dynamics of those blackbody interactions as they happen. It's not just about measuring the average temperature anymore. We can actually track how the temperature is changing over incredibly short timescales.
Wow. So we could literally watch the temperature change in a fraction of a second. What kind of things could we learn from that?
Oh, we could study things like explosions, chemical reactions, all kinds of fast processes. We could even look at the dynamics of living cells. See how the temperature fluctuates as they do their thing.
Like a high-speed camera, but for heat. This is amazing. It feels like we've just started exploring what this technology can do. What other frontiers are out there for Rydberg thermometers?
One area that's really exciting is extreme environments. These Rydberg atoms are incredibly sensitive, right? So we could potentially use them to measure temperatures in places where normal thermometers just wouldn't survive.
Like the inside of a fusion reactor
Uh,
or the surface of Venus.
exactly. And because these thermometers rely on light, we could even measure temperatures remotely, even in the harshest environments.
It'd be like having a thermometer that's basically indestructible. But is there a limit to how hot or cold we can measure with these things?
That's a good question. Right now, most Rydberg thermometers work best around room temperature. But scientists are working on expanding that range to both higher and lower temperatures.
So we can measure a cup of coffee, but not the sun yet.
Uh-huh. Yeah, pretty much. But we're making progress. To measure those extreme temperatures, we need to find different Rydberg atoms, atoms that are sensitive to different frequencies of blackbody radiation.
So it's about finding the right atom for the job, like tuning our atomic antenna to pick up a different channel, and each channel corresponds to a different temperature.
Exactly. It's all about finding the perfect atomic thermometer for the job. one that can handle whatever we throw at it.
This is really cool stuff. But I'm guessing it's not all smooth sailing, right? What are some of the roadblocks that researchers are running into as they try to make this happen?
Well, one of the biggest challenges is just improving the signal-to-noise ratio. We're dealing with these super subtle atomic transitions, and any kind of stray noise from the environment, the equipment, whatever, can mess things up, make it really hard to see what we're looking for.
So it's like trying to have a conversation in a really noisy room.
Yeah, it's like trying to hear a whisper during a hurricane. We've got to find ways to amplify that signal and get rid of all the noise.
So what are some of the strategies?
One really promising approach is to use quantum entanglement.
Entanglement, that's where two particles are linked together, right? Even if they're far apart. How does that help?
Entanglement basically lets us create these correlations between two Rydberg atoms, and that can make our measurements more sensitive, less affected by that background noise.
So it's like having two spies working together.
Yeah.
They can share information and uncover secrets that they couldn't find on their own. Pretty cool. So entanglement is one approach, but are there other things researchers are trying?
Oh yeah, we also need to reduce the noise at the source. That means really carefully engineering the whole setup. Better vacuum pumps, shielding the atoms from stray electric and magnetic fields, minimizing vibrations, all that stuff.
So you're hitting the problem from all angles.
You got it.
Okay, so signal to noise is a biggie. Anything else?
One thing that's often overlooked is the need for standardization. Right now, everyone's kind of doing their own thing, different setups, different methods, which is fine when you're just exploring the basics, but it makes it really hard to compare results from different labs and to move the technology from the lab into the real world.
Right, everyone needs to be on the same page if this is going to be useful.
Exactly. Standardization builds trust, and it makes it easier for companies to use this technology. So we need clear protocols, guidelines, how to build these things, how to calibrate them, how to use them.
So who's working on this?
It's a team effort. National Metrology Institutes, companies, researchers, they're all working together to define those best practices, trying to build a framework that will really get this technology out there.
It sounds like there's a lot of energy and excitement in the field. I can't wait to see where Rydberg Thermometry is in the next few years. It's going to be amazing.
I agree. I think we're going to see some incredible breakthroughs.
Well, we've talked about the amazing applications and the bright future of Rydberg Thermometry, but before we wrap up this deep dive, I think it's important to just step back for a minute and think about what this technology really means. What makes it so important? It's pretty amazing, right? Atoms acting like antennas, lasers shooting electrons into these huge orbits. And we could measure the temperature of, well, anything. A single cell, a distant star.
It really shows you how quantum mechanics, something that can seem so out there and complicated, can actually lead to some really practical technology, and it can change how we understand the universe.
Yeah. I mean, think about it. Temperature is everywhere. It's such a basic idea. But for so long, the only way we could measure it accurately was by using materials that could change their properties.
Right, like how much mercury expands or the resistance of a wire. We were limited by the materials themselves, but with Rydberg thermometry, we can finally break free from that.
We're finally tapping into the universe's own way of measuring temperature, a scale that's based on these fundamental constants, not on some random material.
Exactly. And that's what makes this so revolutionary. It's not just like a small improvement. It's a totally new way of thinking about temperature.
It's like we've discovered this whole new language, a way to communicate with the universe on a deeper level.
Huh. I like that. And like any new language, it takes time to learn it. But as this technology gets better, more user-friendly, we'll see more people who can speak this quantum language of temperature.
Imagine that. What if Rydberg thermometers were as common as our digital thermometers are now?
That's the dream. Quantum-level accuracy available to everyone, not just in some fancy lab.
It'd be incredible. Everyone, from scientists to everyday people, could have access to these super precise measurements.
Think about what that could do for healthcare, for the environment, for manufacturing. We could monitor the health of the planet, control industrial processes really precisely, diagnose diseases way earlier.
Wow, that's quite a vision of the future. Measuring temperature would become a way to understand the world around us better,
Yeah.
from the tiniest cells to those faraway galaxies.
And it all starts with curiosity, with wanting to understand how the universe works and what's possible. That's what science is all about. It's a never-ending journey of discovery.
Well, it's been a fascinating journey today, exploring this amazing world of Rydberg thermometry. I feel like we've only just scratched the surface.
I agree. This is just the beginning. There's so much more to come.
To all our listeners out there, thanks for joining us on this deep dive.
Yeah.
It just goes to show that even when it feels like we're stuck, there's always room for innovation, for breakthroughs. We can push the boundaries of what we know and what we can do.
Keep exploring, keep asking questions, and never lose that curiosity about the world around you. There's so much out there waiting to be discovered.
And on that note, we'll sign off for today. Thanks for listening, and we'll catch you on the next deep dive.